Hello student, how are you doing? In this short video, we're gonna talk about change of variables. This video is extremely important and is very useful to many students, especially who they are in a STEM field. Because throughout Calculus 3, when we talk about multivariables and when we talk about triple or double integrals, sometimes students had difficulty to integrate over a region if the region either x or y was changes. And if this one was y equal to x squared and this one was y equal to x, here the point of intersection is 1 and 1 and 0 0, and then here you have to make your x fixed, but my y varies. And the student, many occasions they said, I don't like double integral or triple integrals when the limits they varies. I like them when x is fixed and when y is fixed. I said, well, I'm sorry, 3 to 4. Well, when x is fixed, you go from 2 to 4, and this one is 3 to 4. You're talking about rectangles, because both, when you talk about x's and y's, are always the same. But in here, see, your y are changing. Here your x are not the same throughout the region for every rectangle. Therefore, no matter how many rectangles you divided into, all of y are the same. And the students were so happy when they see these lower limit and upper limit are fixed numbers. And many occasions they said, is it possible whenever we do have lower limit, upper limit are not fixed and they varies, can we fix them? That's called change of variables. Yes, you can. I'm going to give you a few examples before even I start talking about the lecture I'm going to present. Remember in Calculus 1, you had sine of quantity x squared. Let me put the x right here and dx, and you were trying to find the antiderivative. What did you do here? You made the x squared a u. Then you have to be able to find your dx, and you said 2x dx is a du. You didn't have the 2 over here. You had the x, but you didn't have the 2. That's the factor that you have to add in order to change a variable from x to a u. Then change of variable, always you are requiring a factor. And in this case, and remember, many cases factor is 1. Doesn't mean you don't need it. In many cases, because it's a single variable, the factor is a matrix 1 by 1. And the determinant of that matrix is 2. Somebody said, why did you talk about matrix? Because remember, whenever we had a region and we had x squared plus y squared, let me put them at the radical, you knew that this one was not integrable respect to x, it was not integrable respect to y, because you needed the x in here. In order to do it respect to x, you need a y in here. You said, let's change the variable from a Cartesian to a polar, and you replace here r dr d theta. Where did r that come from? That r is pretty much that number 2 that you multiply and divide it over here, because you have to multiply it here by 2 and divide it by 2. Where did that r come from? And this one from a rectangle, you changing it to a sector, and that region becomes circular, which is, this is your theta 1, theta 2, R1 and R2. R1 and R2 is not a radius, is not a region, is a radius. Let me tell you where that R came from. Whenever you go from a Cartesian to polar, X is a R cosine theta. Then X is a function of R and theta. Your Y is also a function of R and a theta. These are called multivariable function. It's different from single variable. You got to do partial derivative. In here, I have to take the derivative respect to R, and I have to take the derivative respect to theta. What is the partial derivative of X respect to R? Is cosine theta. What is the partial derivative of Y respect to R? Is sine of theta. But I do also have a theta. What is the partial derivative of X respect to theta? Negative R sine theta. What is the partial derivative of Y respect to theta? Is R cosine theta. In here you had a single variable. The factor you needed, it become a 1-by-1 matrix, and I'll find the determinant. This is two variable. The factor you need is a determinant of a 2-by-2. What is the determinant of that matrix? This is R cosine squared theta plus R sine squared theta, because negative times negative, because you're doing it backward. And here R is a common factor, and cosine squared theta plus sine squared theta is 1. You got that R, and that's the R we're talking about today. But somebody said, okay, but you also told me whenever I have triple integrals, I can go from volume, which is dz, dy, dx, I can change this one to a spherical coordinate. And it was d rho, d phi, d theta. Where this factor came from? Remember, the factor for the polar was a R. The factor for single variable is a constant. But where this came from? Very easy. X in a spherical coordinate, this is R cosine theta, but R is sine of phi, cosine theta. But your Y is rho sine of phi, because that's R, sine theta, and your Z is a rho cosine of phi. I hope you remember those from spherical. This is a function, X is a function of 3 variables. The Y is a function of 3 variables. Z is a function of 3 variables. Somebody said, I don't have a variable. Yes, you can put a cosine of theta to the power of 0. I want to align it with everybody. Then somebody said, in here, I have to take the derivative respect to rho, respect to phi, and respect to theta. Well, you got to do partial. What is the partial derivative of X respect to rho? The derivative of rho respect to rho is 1. You have sine of phi, cosine theta. What is the partial derivative of Y respect to rho? Is sine of phi, sine theta. What is the partial derivative of Z respect to rho? Is cosine of phi. I took the partial derivative of all 3, X respect to rho, Y respect to rho, and Z respect to rho. Here, I need partial derivative of X respect to a phi. What is the derivative of sine of phi? Cosine of phi. Therefore, you have rho cosine of phi cosine theta. I need the partial derivative of y respect to phi. Rho cosine of phi sine theta, because derivative of sine is cosine, derivative of sine is cosine. But what is the partial derivative of z respect to phi? Is rho negative sine of phi. Also, I have a theta. What is the partial derivative of x respect to a theta? Cosine theta is negative sine, is negative rho sine of phi sine theta. Negative sine theta, sine phi, and a rho. I need the partial derivative of y respect to a theta. Derivative of a sine is a cosine. Is rho sine of phi cosine theta. Not sine to cosine. I'm doing it respect to what? Respect to theta. The derivative of sine is a cosine. That's right. What is the partial derivative of z respect to a theta? 0. If I find the determinant of that 3 by that 3 matrix, it must give me that factor. Therefore, from today you have to know, when you are changing a variable, if it's a single variable, you have a matrix which is a 1 by 1, find a determinant. If it's a 2 variables, a matrix 2 by 2, find a determinant. 3 by 3, 3 variables, 3 by 3, 4 variables, 4 by 4, a determinant is a factor you have to add. Therefore, somebody said, what is the determinant of that matrix right here? Well, I have to do expansion by minors. I'm going to expand along any row or any column. I'm going to do it row 3 because I have a 0 here. Therefore, please pay attention what I have to do. Positive, negative, positive. Then I'll put plus cosine of phi, that's my factor, times the 2 by 2 matrix. I need that 2 by 2. Give me the determinant. Rho squared cosine of phi sine of phi cosine squared theta. Minus negative times negative is a positive. Rho squared cosine of phi sine of phi sine square of a theta. I took care of this, but what I see right here, a common factor, this is a common factor. When I get the factor, what do I get? I say cosine square plus sine square. Cosine square plus sine square is 1. Therefore, you have cosine of phi times rho squared cosine of phi sine of phi. Cosine square plus cosine square is 1. You put 1 here. And this is cosine square of phi sine of phi, and I have a rho square. That's for this one. I need to do this. Positive, negative, positive, and negative. Therefore, I have a negative. Then this is my factor, negative rho sine of phi. I need a 2 by 2 matrix. This is right here. This is rho sine square of phi cosine squared theta minus negative times negative is a plus rho sine square of phi sine square of a theta. I'm sorry. Do you see what I did? I took that one, I eliminated this row and this column, I multiplied these two, minus the product of these becoming plus is right here. Negative times negative is a positive. Therefore, I have a row here and a row here. That's rho squared. Because both have row. I have a sine of phi in all of them. I'm going to factor sine. I have a sine of phi here. I'm going to factor another sine of phi. What I have here Okay, in here I have sine squared plus cosine squared. Let me not do that. Let me write rho sine of phi, and I'm going to factor rho sine square of phi. Cosine squared plus sine squared is 1. Between these, I have rho square sine cube of phi. This one is for that one, and this is 0. Therefore, I need this one, and I add them together. I have rho square cosine square of phi sine of phi plus rho squared sine square of phi sine of phi. I just wrote the power of 3 just like that because I want to get sine of phi as a common factor. And when I get a sine of phi, I get cosine square of phi plus sine square of phi, and that's 1. Do you remember that factor? These all, the rho square sine of phi, these are called Jacobians factors. Jacobian is named after German mathematician called Jacobi. Jacobi known for his work in many areas of mathematics, but his interest was in integration. It stemmed from a problem of finding circumference of an ellipse. Therefore, maybe he took an ellipse and changed it to a circle. He knew how to find the circumference of a circle. Therefore, he changed the shape. Therefore, what is a Jacobian factor? There are many occasions you are integrating over some region, which region is very complicated. I'm going to make this region right here, see, and that region. That region, if I want to integrate over it, maybe I have a double integral, that's my region, and I want to integrate x squared y over that area. Number 1, that region, you have to cut it in half, because from here to here, this line is above and this line is below. And from here to here, this line is above and this line is below. These are 4 different lines. If you have to break this one to 2 integrals. You have to find that point of intersection. You have to find that point of intersection. You have to be able to find that point of intersection. Therefore, finding area of a region, and then you have to make the x fixed. The y varies. The y, the bottom one is here, the top one is here. Let me make some example for those stuff. This is a rising line. I'm going to say y equal to x plus 4. And I'm saying these are parallel line, x plus 1. But these are falling line, y equal to, I'm going to make it easy, negative 1 plus a 5. And the other one, I'm going to put y equal to negative x plus an 8. I'm going to let you know how easy I'm going to do that integral. Instead of that region. Look at how I'm going to change variable. I'm going to bring that x to other side. And I'm going to bring that x to other side. And I'm going to call y minus x a letter u. I'm sorry. Therefore, this is my u. And I'm going to, I don't know what I'm going to call that axis. My u go from 1 to 4. And right now, I'm fixed. My u is fixed. Somebody said, what do you do with this line? I'm going to take the x to other side. I'm going to take the x to other side. I'm going to call y plus x a v. That's my v axis. And I'm going to go to 5 to an 8. And I'm going to use that region. And I'm going to do a double integral. 1 through 4, 5 through 8. Don't you love that? But somebody said, what do you going to do for x squared? I'll let you know in a minute. What you gonna do for the region? I know for a minute, because I change a variable, I need one of those factors. Then let's see what am I gonna replace for x squared and y. Remember, u was y minus x. V was y plus x. If I combine these equations, u plus v is 2y. Then my y is 1/2 of u plus v. I know what my y is. But somebody said, what you gonna do for your x? I'm gonna go right here and I'm gonna multiply all this by negative. Negative times negative is a positive, and I kill the y. And I'm gonna say v minus a u is equal to 2x. And my x is 1/2 v minus a u. I know what I'm gonna replace for x. But somebody said, what are you gonna replace for dy dx? Are you gonna make this one a polar coordinate? No, sir. Are you going to do a spherical? No, sir. In here, you need to know, since your x is v minus a u over a 2, that's two variable, you need a u and a v. I need a partial derivative of x respect to a u for u, and partial derivative of y respect to a u. But what was my y? My y was u plus v over 2. And in here I need partial derivative of x respect to v and partial derivative of y respect to v. Then whatever the determinant of that matrix is a factor that you're adding to do du dv. Just like r dr d theta. Just like d rho d phi d theta. These are the factor you need to do. What is the partial derivative of x respect to u? Negative 1/2. What is the partial derivative of y respect to u? 1/2. What is the partial derivative of x respect to v? Is a 1/2. And what is the partial derivative of y respect to v? Is a 1/2. What is the determinant of that matrix A, if I call it a matrix A? That's the factor. That's come in place of r. That come in place of rho square sine of phi. 1/2, negative 1/2 times 1/2 is negative 1/4. Minus a 1/4. And that's negative 2/4. That is a negative 1/2. Therefore, instead of dy dx or dx dy, it doesn't matter. You put negative 1/2 du dv. Negative 1/2 du dv. And u and v are fixed. Then you said, I want to integrate that over that ugly region. I'm going to change it to that region. And I'm going to make my y go from my u go from 1 to 4. My v go from 5 to 8. Instead of x squared, I'm going to write v minus a u squared over a 4. I squared it. Instead of a y, I'm going to write u plus a v. And negative 1/2 du, not du, because du is at the end, dv du. 2 times 4 is 1/8. I bring the negative 1/8 out. And I'm going to write 1 to 4, 5 to 8. That becomes v squared minus 2uv plus a u squared multiplied by u plus a v. Then your answer is u v squared minus 2u squared v plus u cubed plus v cubed minus 2u v squared plus v u squared. I move the negative 1/2 outside. I have dv du. I'm going to do it with respect to v. u v cubed over 3 minus 2u squared v squared over 2 u cubed v minus plus v4 over 4 minus 2u v cubed over 3 plus v squared over 2u squared. But these have to be integrated from 5 to 8. I bet you can put 8 for the v, which is not a big deal, and you could put 5 and subtract them. Then you're going to get everything in terms of u. Then you're going to integrate it from negative 1/8, 1 to 4, whatever it is respect to u, and find it. I'll let you finish that problem. But do you see how important it is, the change of variable, which change of variable always looking for a factors, and that factor, if it's a single variable, is a determinant of a 1-by-1 matrix. If it's a 2 variable, is a determinant of a 2-by-2. If it's a 3 variable, 3-by-3. But when I said determinant of the partial derivative. If it's 2 variable, you're going to have 4 partial derivative. U is a function of, x is a function of u and a v, and y is a function of u and a v. Therefore, you have to do 2 partial for u, 2 partial for v. And find that one right here. Therefore, let's do a single easy problems. And for that, one of the easy problem, let me how much it is. It's 27 minutes. You know, maybe if we pick that one right here and said x is equal to 1/2 u plus a v, and no, I don't like that. I'm gonna do this one. This is from a textbook. That's my region, 60 xy dA, but my x is 1/2 u plus a v, and my y is a function of 2 variable, is negative 1/2 u minus a v, and they are giving you that region. I'm not going to finish the problem. Hopefully you'll be able to finish the problem. That region is 1 and 0. I bet you this is negative 1 and 0. I bet you this is 0 and 1, and this one is 0 and a negative 1. They gave you that region, but you have to automatically know that's the equation of a line. And what is the slope? 1 minus a 0, y2 minus a y1, over 0 minus a 1. Your slope is negative 1. That's your y-intercept. Then your y is negative x plus a 1. I bet you these two are parallel to each other. And the y-intercept is negative 1. Therefore, this is y equal to negative x minus a 1. Therefore, I bet you this one is y plus x equal to 1, y plus x equal to a negative 1. I'm going to call y plus x my u. And I go from negative 1 to a 1. I'm changing it to a rectangular region. Rectangular region. But somebody said, what is this? Rising line. y2 minus y1, 0 minus negative 1, over 1 minus 0. I bet you the slope is 1. Y equal to x minus a 1. And I bet you this one is y equal to x plus 1. Then y minus x is negative 1, and y minus x is 1. I call y minus x a v, y minus x a v. Therefore, my v goes, oh, I made a mistake on that u, I'm sorry. Your u is the x-axis. I go from negative 1 to 1. because that was, I call this one a u-axis. This is a v-axis, and my v-axis, I go from a -1 to 1. See, right now it's fixed, and I'm gonna write right here -1 to 1 and -1 to 1, but instead of dy dx, I'm gonna put dv du. I do need a factor, but also I have 60. I'll put a 60 right here. But what is my x? My x is right here. I pull the 1/2 out. My y is here. I pull the 1/2 out, that become a 4th. And when I multiply these two, these are conjugate. That become u squared minus a v squared. Then if you give me the factor, I'm done. The factors I need for u and I need for v. I need two partial derivative, two partial derivative. What is the partial derivative of x respect to a u? Well, I call this one a u. Therefore, I have not solved for x and a y. I said your y plus x is u. And I said y minus x is a v. Oh, u plus a v is 2y. Oh, they already gave us in here. I'm sorry. They gave it to us. And I could find it myself. Therefore, what is the partial derivative of x respect to u? 1/2. What is the partial derivative of y respect to u? -1/2. What is the partial derivative of x respect to v? 1/2. What is the partial derivative of y respect to v? Plus 1/2. And the determinant is 1/4 minus -1/4. And that become 2/4, and that become 1/2. The factor here you need is a 1/2. Then from today, every time you change the variables, if it's a single, you need a determinant of a matrix one by one, and you just do the derivative. If it's double or triple or more than one, you have to use partial derivative. If your quantity is a function of two variables, you need two partial derivative here. Your y also have two partial derivative, that's make it a 4, a 2 by 2. If it's a function of three variables, you need 3 by 3 with three variables. And the determinant is a factor that you have to do. Therefore, at the very end, let's talk. Say, what is dy dx? That's a Cartesian. What is in polar coordinate? Is dr d theta. But what is the Jacobian factor right here? Is an r. Dz dy dx. That's a Cartesian volume. I can change this one to a spherical coordinate. A spherical coordinate is d rho, d phi, d theta. But what was the Jacobian factor? Because x is a function of three variables, y is a function of 3, z is a function of 3. That was your rho squared sine of phi. Then from today you have to know, if you go from dy dx to dv du, you will need a factor here, which that factor come from partial derivative of x respect to u, partial derivative of y respect to u, partial derivative of x respect to v, and partial derivative of y respect to v. What happens if it's a three variables? You need a 3 by 3. Whatever the determinant of that matrix is your factor, and these are called Jacobian factors. And it is very important in a STEM field. Thank you, and I hope you enjoyed the video. Have a great day.